Swayam Prabha. Digital India. Educated India.
So today we will continue our discussion on the properties of metals, basically what they mean, how to determine them and so on. I will emphasize a few points which I had already talked about in the previous lecture, but then many times these points, if they are read only once or if they are heard only once, they are often forgotten over a period of time. That is why I would like to emphasize them so that they should never be forgotten. So first thing is that when we talk about mechanical behavior, we talk about response of a material to a stimulus in the form of loading. So loading is the only stimulus for structural materials which is of interest. So we have different environments under which the materials function. There could be seawater environment, there could be a polluted environment, it could be let us say salts or different kinds of solvents could be there, nuclear radiation could environment. So there are variety of environments under which the materials have to serve. In fact, the environments range from very noble environments where we have inert gases or relatively less reacting materials or less non-reacting environment or inactive, chemically inactive environment, and in other spectrum we have a highly reactive or highly corrosive environment or highly deleterious environment which leads to degradation of the material very rapidly. So loading can take place under all kinds of situations. For example, you have pipelines carrying sulfur dioxide, hot sulfur dioxide gas. Sulfur dioxide is known to be highly pungent and highly reactive, and moisture is always there in the air. So sulfur dioxide could also have some moisture contained in it, and when a pipeline carries this sulfur dioxide at high temperature together with some moisture meaning at those temperatures it would be steam, then you would get a very obnoxious type of environment under which the material has to work. So this loading will take place under a very obnoxious environment, and which will attack the integrity of the material as well as expect the material to support the load. So loading is something that is in any case there irrespective of the kind of environment, and it is important to understand the mechanical behavior of the material under these different kinds of environments. Loading itself can differ, mechanical loading can differ with respect to time. For example, you have a monotonic loading, so the load continues to increase with time, as in case of a tensile test. Sometimes the load remains constant. Let us say you have a boiler, you start the boiler, the pressure goes to a certain level, the boiler is subjected to that loading for a long period of time. So now the service conditions are that of temperature, very high temperature, as well as load for a prolonged period of time. Plus there could be impurities in water, constituents in water, which would result in some corrosive action of the chemicals in the water on the boiler material, on the boiler drum. So now the load increases up to the pressure of the working pressure of the boiler. It is sustained for a period of time, and then when you decide to maintain the to carry out maintenance operations on the boiler, you would like to shut it down for maintenance and you bring down the pressure as well as temperature to atmospheric temperature and room temperature, atmospheric pressure and room temperature. So, you need to therefore understand how the material will behave during this period of loading, sustained loading, right. So, you would like to assess the response of the material. Usually most of the structural materials are subjected to loading of different kinds. I talked about a sustained loading. There could be load fluctuations as well. So, you could have changes in load, variations in load. Let us say you have a shaft which is a shaft of a machine tool like a lathe or any other machine where the shaft experiences a certain amount of load. So, you have what is called as rotating bending type of fatigue loading coming into play, because if you look at the shaft, it is being bent as well as rotated. So, you have a shaft which is rotated at a certain RPM and it also deflects under load, and this deflection results in tensile compressive variation in the strain. Why? Let us see. Now, let us say this is this is only bending, right. So, at the outer fiber at the top you have a loading resulting in tension, at the lower fiber you have in compression. Now, imagine this being rotated at a higher speed. So, now at some point this lower fiber will go to the top and the top fiber will come to the bottom, and since the direction of application of force remains the same, you will find that what was under compression earlier now is under tension, and what was under tension comes under compression, and this will happen with the frequency at which the shaft is rotating. So, supposing the rotation of a shaft is at 5000 RPM, then this changes will happen at 5000 times. So, you will experience these tension to compression changes taking place 5000 times in a single minute. So, the frequency at which the loading changes direction is typical of certain kinds of equipment, certain kinds of shafts especially. So, now from the boiler where you had a load for a long duration, you have a shaft which has got loading which is alternating between tension compression. So, this is called as rotating bending type of loading. Similarly, there are different kinds of equipments which would be subjected to loads, let us say shear load or compressive load. So, there are there are machine elements which would be subjected to this shear compressive type of loads, and we expect deformation to be purely elastic in nature. So, when the material is in service, you want the deformation to be purely elastic, and therefore, the elastic stress strain ratio becomes important, and the higher is the value of the slope, that is E, Young's modulus, lower is the deflection or lower is the strain. That is because even if the stress rises to a very high value, a high slope in E ensures that the strain is very small. This becomes important because if you have equipment of, let us say, infinite stiffness means infinite Young's modulus, then what happens is it will not deflect at all, which means that the machine elements will not change their shape at all. Now, these although the strains are recoverable, so if the load is removed, the strain is completely recoverable, but still the fact that the material is changing shape under load, that itself can create a problem over a period of time, and this is due to what is called as fatigue. What I was telling you here applies to our discussion, meaning that let us say you have a beam which is subjected not beam, you have a shaft which is subjected to rotating and bending. So, the shaft rotates as well as there is a bending moment acting on it. Now, the deflection which I talked about here is elastic, meaning if the load is removed, it will come back to its original position, but then you will have lot of accumulated damage taking place, as the shaft goes from tension to compression, so upper fiber in tension, lower fiber in compression, the upper fiber goes in compression, then lower fiber goes under tension. So, this alternating types of stress coming on the shaft will result in accumulated damage because of the strain. Supposing the shaft is of infinite E, then there will be no strain, and then the fatigue life will be also practically infinite. But then that is not the case with any practical material. So, you take a practical material, it will always deflect. Deflection may be immeasurably small, but then the material will always deflect, and due to that it will result in elastic strains, tension compression at the top surface as well as at the bottom surface, and as a result you will find damage accumulating in the shaft. So, this is a very important aspect for structural materials. Deflection has to be only elastic, it is recoverable in nature. Now, when we try to make the product, when we try to make the entity that is supposed to withstand structural loads, for example, a turbine blade or a turbine itself, the turbine during functioning will undergo elastic deflections, but when you actually want to shape the turbine blade from let us say single crystal to the kind of shape of the turbine where you have different angles, entry angle, exit angle and so on, there you need to deform it, and therefore you need to take it beyond the yield point of the material. So, elastic deflection is not enough. So, elastic deflection will get removed or it will be recovered completely, but now what you want to do is, while manufacturing the turbine blade, you need to change the shape of the material permanently, so that the blades have a shape giving the right kind of entry angle and the right kind of exit angle for the gas or steam or whatever fluid that you might be using. So, that is why it is important that the permanent change in shape during manufacturing and elastic deflection during service are clearly understood. The distinction between these two is clearly understood. Now, when you have permanent deformation or plastic deformation, material behaves in a non-linear manner. So, here this is called as linear behavior of material, this is called as non-linear behavior of material. So, if you want to determine the rate of change of stress with respect to strain at any given point of time here, then you need to draw tangent to the curve, so that you can get the instantaneous rate of change of stress with respect to strain. So, here you have the stress strain relationship where the slope E is constant, here the slope E is varying. So, now here in this kind of mechanical behavior, the slope of the tangent depends upon where the tangent is drawn. So, if you draw a tangent somewhere there, the slope is very much different as compared to the slope over here, and therefore, the extent of deformation also governs the rate of hardening, as it is called, because when you say the stress is increasing with strain, we call it as rate of hardening of the material with respect to strain. So, essentially this will be a measure of strain hardening of the material. So, now we have a repertoire of material, lots of materials which are possible, and we have seen that if we give a stimulus, that is you increase the pressure to its or force to its working condition, working in service conditions, sustain it for a certain period of time and then take off the force that was applied, it will result in a stress which will rise to its in service condition level, get sustained over a period of time, and then the stress will fall to 0 as the load is removed. So, load is the external stimulus and stress is the response of the material internally generated to sustain that load. So, basically to achieve equilibrium between the externally applied load and the material. So, so the material reacts in the form of stress. So, the reaction of the material is in the form of stress, which is in response to the load being applied, and this load is sustained for a period of time and it is brought to 0. Now, the difference between the stress and pressure, although the units are the same, is that pressure acts on exterior surfaces, and the stress on the other hand acts internally, is generated internally. On the free surface, therefore, stress is 0. On the in the interior parts or interior surfaces, you can have stress generated in response to the load or pressure conditions acting on the surface. So, for example, you take the example of a boiler. You have a boiler drum, the internal surface experiences pressure. So, the surface experiences pressure, but the stress is generated all over the material. So, all over the thickness of the boiler plate, the stress is generated, and if the boiler plate is too thin, the stress can be of such a large level that you can have permanent deformation of the boiler, which is not acceptable. So, what it means is that the stress is the response of the material, and it can be generated to a level depending upon the cross section of the material, the thickness of the cross section which you might have taken in the context of the boiler plate. So, you need to therefore make sure that your product is designed sufficiently well, so that the stress coming on the product in service is well below the yield strength of the material, so that in service the material does not yield. So, in case of boiler, the in service condition is certain temperature and certain pressure inside. So, naturally the boiler plate should be sufficiently thick, so that the stress coming on the in the boiler plate, the maximum stress generated in the boiler plate is much lower than the stress that is required for permanent deformation of the boiler plate at the service temperature. So, now different materials obey different give different responses. You have an ideal elastic solid over here where the elastic strain or permanently recoverable strain is fully recoverable strain is therefore shown over here. So, at the end of the cycle, if we call this a cycle, at the end of the cycle the strain is 0, the strain that is retained by the material is 0. So, these are typically materials which are of course metals, but then there are metals below yield stress. Then you have thermoplastics which are well below glass transition temperature, because thermoplastics are essentially chains of hydrocarbons, and so these chains get extended and they come back to their original position, and this happens provided the temperature is below the glass transition temperature. And then thermosetting plastics, ceramics and glasses would obey this ideal elastic solid stress strain relationship. On the other hand, you have here another response of the material, because now you are applying a certain amount of stress, but now the material is the yield strength of the material is much lower than the stress which has been applied over here. As a result, it changes into a plastic state, and on the removal of the load here, you see that there is some permanent deformation that is retained. So, the deformation does not fall to 0 as in case of elastic solid. Here you have an elastoplastic solid, where the difference is that the elastic strain is partly recovered. It is not fully recovered, it is partly recovered, and there is some amount of plastic strain that is retained. So, elastic strain is some elastic strain is always there, and then there is plastic strain retained by the material. So, permanent deformation is present, and so these are ductile metals above the yield strength of the material. So, essentially this is the kind of response. Now, if you take a high temperature material, if you go to high temperatures, then the materials often become viscous. I had told you that the grain boundaries become viscous and they start responding to strain rate. So, the strain versus time will have a slope continuously varying with time, because these materials respond to the strain rate meaning that as the strain increases, the strain rate changes, and therefore the material will respond in terms of changing strain, because as you see the stress is constant, the stimulus is constant, but the strain response is changing, because initially the strain increases very rapidly in the response to the stress, but then because of viscous effects the strain rate increases tremendously, and therefore the rate of change of stress continues to drop. So, the rate of change of strain rate therefore continues to drop, because the viscous response of the material results in hardening of the material, and therefore the strain rate continues to drop. In the initial phase the strain rate was 0, and then material had to start from the 0 strain rate. So, immediately as the stress was applied, it responded with a very high strain rate, but then as the strain rate was high, the hardening of the material was also very high in response to the due to viscoelastic response, because now when we say viscous fluid, it means that it hardens with strain rate. So, the very definition of viscous material is that it hardens or increases in strength with respect to strain rate. So, here there is an increase in the strength of the material with strain rate, and then as a result, for a given stress, the load required to deform continuously increases, and the strain rate therefore falls. It keeps falling up to a point, and then when the load is removed, again the material does not come back to its the strain is not recovered immediately. There is a time lag between the two. So, viscoelastic response or viscoelastic strains differ very significantly as compared to the purely elastic solid. So, here you see that there is a drop over a period of time. Okay. Here is still plastic strain is retained, some plastic strain is retained, and the recovery of elastic strain is not as instantaneous as it is in these two cases. So, here the elastic recovery is depend upon the strain rates, because once the load is removed, then the response of the material is delayed. So, the strain rate starts falling down. So, initially there is a rapid reduction in the strain here. So, the elastic strain gets rapidly recovered, but then again the viscous effects come into play, resist that also, and then the rate at which the strain gets recovered keeps falling, and then it is the least at this point over here. So, you always have a certain amount of plastic strain, whereas in case of a rubbery type of material, you have instantaneous response. So, here you do not have the viscous effects. So, the viscous effects are present here, but here there are no viscous effects. So, as a result you have immediate increase in strain corresponding to the stress. Then there is an increase in the strain even under constant stress. So, even if the stress remains constant, the strain continues to increase. So, this is the difference between the between this and that, and then you have immediate drop in the strain as your load is removed or the stress is removed, but then there is a retention of some amount of strain, which is the plastic strain, which this is non recoverable, or which is also called as a plastic strain. So, elastomers, rubbers, and some thermoplastics at temperatures above viscoelastic range result in this kind of behavior. So, this way one can go on understanding the behavior of different materials. You have another material like thermoplastics and glasses well above the glass transition, and metals above 0.5 Tm under special conditions. So, here you have what is called as an immediate increase in the strain rate, and then you have the hardening of the material due to strain rate. So, here you have hardening due to the strain rate increasing due to viscous effects. Okay, you have hardening due to viscous effects. Now, here you are not talking about viscoelasticity. The difference between this and this is that here it is viscoelastic in nature, here it is viscoplastic in nature. So, there is a significant amount of plastic strain that is retained over here. So, you have thermoplastics and glasses above the Tg, and so they become a kind of viscoplastic. And so, here also you have a similar situation where this rise in strain rate is non-linear in nature. So, this is under creep and plastic strain increasing with time. So, the plastic strain essentially creep refers to an increasing plastic strain with time, and therefore, you can have some elastic recovery, but most of the strain is retained as plastic strain. So, in creep the most of the strain is plastic in nature, and then and here the as the stress increases, the and you maintain it at that level, the strain is and the strain is constant. So, you deform the material to a constant strain. So, here this is a completely different situation. The material is deformed to a certain constant strain, the stress level keeps dropping. So, supposing you have loaded a sample, the stress level as in thermoplastics, you load them up to a particular strain level and leave it at that, the stress level will continuously decrease due to these due to relaxation of these polymer chains. So, basically these are the different responses of the material, and that is exploited in actual use for different applications. That is what I wanted to emphasize by this. The relative densities determine the weight. So, we want to determine the strain to weight ratio, and so these composites, for example, have the least amount of density and therefore least amount of weight for a given volume, and therefore you have if you can have very high strength with composites, then the strain to weight ratio, typically in aerospace structures, this would be of great advantage. So, we have discussed this already, and then I will come to the issue of the yield point, which we had discussed earlier. So, I will just come to a worksheet where I will show you how it is determined again, so that you have no questions on that. Yeah. So, this is the elastic portion, and you need to determine the slope of this elastic portion. So, Young's modulus has to be first determined, and so that for that you need to select the elastic zone. So, here we have selected the elastic zone, stress versus strain. So, this is stress here and strain over here. Under elastic conditions, with true stress and engineering stress are the same, because true strain is practically equal to the elastic strain. There is no change in the cross section, and therefore, the true strain and elastic strain are practically the same. So, that variation can be in the in 7th or 8th decimal place, which is not of interest to us. So, now you get the value of E, and then you have you plot these terms epsilon minus sigma by E. So, what it means is that supposing I am trying to evaluate this as a possible yield point for the material. So, I draw a line which is parallel to this line. So, I draw a line parallel to this line, which let us say hits the x axis here. So, now I have this as the recovered elastic strain, I have this as the recovered elastic strain. So, so this is equal to sigma by E. E is the Young's modulus, and sigma is the stress over here. So, sigma by E is the recovered elastic strain, and so what I am left with here is the plastic strain. This is the plastic strain, right, and this plastic strain has to be 0.2%. So, now if I subtract epsilon minus sigma by E. So, my sigma by E as a result of this line drawn parallel to this Young's modulus line comes here, then this is my sigma by E. These two are my sigma by E. So, epsilon minus sigma by E is my plastic deformation which has been retained to the and I say that material has yielded when this plastic deformation which is retained reaches 0.2%. 0.2% is the plastic deformation that has been reached. So, that is the 0.2% proof stress. So, you can specify the proof stress as say 1% proof stress or 0.1% proof stress depending on the, what you want, but then the standard value which is worldwide accepted is 0.2% proof stress. So, you take 0.2% here. Now, the logic here is that all grains do not yield at once, and therefore, the some of the grains reach yield point, but few other grains might not reach yield point in a polycrystalline material. So, when most of the materials we use are polycrystalline in nature, they are each grain is surrounded by many other grains, and due to that there is a constraint that is imposed on a grain due to surrounding grains. So, now what happens is, if the surface grains reach the yield point, the interior of the sample has not reached the yield point yet, because the yield point of that is much higher compared to the yield point of the surface grains. So, now you have surface grains which might have yielded, but the interior of the sample which has not yielded. So, that is the reason why you need to give 0.2% plastic strain, so that you can be sure. So, for all practical purposes you can be sure that the entire sample, all the grains in the sample have reached the yield point. So, that is the reason why we have 0.2% offset or 0.2% proof stress. So, now this is the parameter which I have plotted for the stress strain curve. So, you have in the elastic range epsilon minus sigma by E, and then this keeps on increasing, this keeps on increasing. Now, this is the third decimal here, and now you see here that the it has reached 0.00199. So, 0.002 and less than 0.002, here is slightly more than 0.002. So, then I interpolate between these two values, and then I have my yield strength as 472.71. And then from this time onward, onwards I start applying my plastic deformation formulae. So, I plot ln sigma versus ln epsilon, because I want to fit the plastic deformation curve into a constitutive equation sigma equal to k epsilon to the power n. So, this is the kind of Holman equation. So, k is the strain coefficient, n is the strain hardening exponent. So, k epsilon to the power n is my formula in which I try to fit it. So, ln sigma equal to ln k plus n ln epsilon, that is what I get as the equation. And so, I then use this to calculate the value of n and k. So, I have r square always beyond 0.99. So, 0.995, 0.998 is good, and I get the value of n as 0.128 and k as 805.127. Now, based on this I recalculate the stress, because now this stress is something I said it is the yield stress, and from this point onwards the plastic strain would start coming into play. So, now I try to predict using this these values of n and k, and using the equation sigma equal to k epsilon to the power n, the stress values in the plastic regime. So, I see that there is an error of about 1, and as I go down the error continues to decrease and then even become negative at some point. So, now I have a very small over prediction or under prediction by a few MPa. Now, if you look at the stress, it is about 476 MPa, the maximum error is about 8 MPa. So, 8 in 473 is a very small error which is tolerable, but then if you want to really use the equation sigma equal to k epsilon to the power n, then it is appropriate to go beyond about 8% of true strain. So, if the strain is beyond 8%, then the error continues to decrease to a very small level. So, if you go down further, it will be a fraction of a percent. So, you have about 3 MPa in over 500 MPa of 526 MPa of stress. So, it is hardly any error that is incurred. So, that is why this equation becomes accurate not at very low plastic strains, but at relatively higher plastic strains, meaning yes, here the plastic strain is comparable with the elastic strain in magnitude. So, here the plastic strain is comparable. So, 0.2% was a elastic strain. I mean, we have assumed that up to 0.2% proof stress. So, the plastic strain. So, here you see that the it is a very small plastic strain, and the plastic strains therefore are comparable with the elastic strains which we had taken here. So, 0.002, 0.003. So, for example, here the elastic strain is I mean the plastic strain is comparable with the elastic strain. So, we had put our yield point at 0.002, this is 0.003. So, so this region is kind of elastoplastic in nature, whereas as you go down you can apply this equation, you can apply this equation sigma equal to k epsilon to the power n with reasonable degree of accuracy. So, so this is what I wanted to explain about the yield point, and now we come back to our discussion about the mechanical properties. Okay. So, you have the yield points of different materials which are given here, and then if you load and unload, you see that I mean this is what is shown over here. So, if you load and unload, now again you have to get the 0.2% proof stress. So, now this is the elastic recovery, and then so if you take a sample, load it up to the certain strain, unload it, and then you reload it, then it will again follow this curve, and then you will find that it will yield here and it will continue further. So, if you were to join this, it will follow on the same curve, except for this cusp which is the result of loading and unloading. So, this is the ideal situation. In reality, what happens is you have unloading from some strain, and then you have reloading taking place. So, there is a slight there can be slight variation, especially if there is if you have unloaded it to a region of compressive strain, then the yield point comes down. So, if you have unloaded the material to a strain below 0, meaning in the other direction, then the material will yield at a lower yield point as compared to what it did during tension. And then when you again load it, it will again yield below the yield point which it yielded under compression here. So, this way the material will undergo softening as you change the direction of stress. So, this is called as Bauschinger effect. Bauschinger effect results in softening of the material, and that leads to a continuous decrease in the yield strength of the material as you keep on changing the direction of the stress. So, that is the reason why I told you that when you have rotating bending of the shaft, or when you have rotating bending type of stress coming onto a machine element, the top surface undergoes elastic deformation to a tensile degree, then on the other side you have compression, and these stresses get reversed say 5,000 times every minute. And so, because of this the fatigue damage can get accumulated. Similarly, now what we are talking about in case of shafts is purely elastic deformation. So, the damage accumulation is extremely slow, but if your material crosses the yield point, then let us say you take a wire and then bend it to a very sharp angle of bend, then there is a plastic deformation in the outer fiber, and when you reverse the stress, the outer fiber will yield at a much lower strain as compared at a much lower stress as compared to the previous cycle. So, naturally it will get softer and softer progressively, and then it will finally break. Why will it break? Because the yield strength will practically come to 0, and then when you just apply some amount of force, it will break into 2 pieces. So, this is the technique we use for breaking a wire. For example, if you subject it to tensile compressive stresses successively over a number of cycles you keep on reducing the yield point of the material due to this Bauschinger effect, and then it will fail. So, if the stress level had been within the elastic limit, it would have continued for a long period of time, then it would not have broken. But since you have gone to the plastic range, the yield point gets affected, the yield point comes down, and at some point it will reach 0 and finally it will break. So, this is one thing that needs to be kept in mind. The Bauschinger effect is a result of reversing stresses, and so if in a rotating bending scenario, if the outer fiber were to cross the yield point, the inner fiber were to cross the yield point, then within few cycles the shaft will start developing cracks from the surface inwards. Why? Because now the surface will get progressively softer and softer, because the direction of stress is changing and the yield point has been exceeded. So, initially the yield point was exceeded in tension. So, in compression it yielded at a much lower yield point. Again, when it was subjected to tension, the yield point was further below. So, this way the shaft will become softer and softer at the surface, and thereby you will have entrainment of cracks develop at the surface, and these cracks will start moving inwards. So, these are the this is the reason how damage gets accumulated, particularly when the stress goes beyond the yield strength of the material. So, the accumulation of damage is very severe when you cross the yield point. Now, here in some of the alloys like copper germanium alloy, what happens is when you unload a material, it has it shows a negative. So, here you see that the recovery is the strain recovery much higher than what would have happened if the stresses were purely elastic, or purely elastic recovery had taken place. So, it is not just the elastic strains which have been recovered, but there is some additional recovery, and so you have this closed loop. So, this is the closed loop, which the area of this loop signifies the energy dissipated inside the material. So, this loop, the area of this loop is due to the energy dissipated inside the material. So, while loading and unloading, you have a different path. So, here the path was the same. So, the energy of the area in this loop was exactly 0 in this case, but here the area is not 0, and therefore, this is proportional to the energy that is dissipated during this loading and unloading cycle, and this will result in an increase in the temperature of the alloy as it undergoes loading and unloading. That is because this dissipated energy will appear as heat. So, this kind of elastic strain recovery is typical of certain alloys, and sometimes you see these things in samples subjected to fatigue, let us say axial fatigue or rotating bending fatigue, basically loading and unloading type of cycles, where so called internal friction results in dissipation of internal dissipation of energy, leading to a finite area of this loop, and therefore, heating of the material during the course of fatigue. So, now you see that the yield strength gets affected not only by the direction of straining, but it also gets affected by temperature. As you see that as you look at these temperatures, you have the different yield strengths and the Young moduli. You have yield strengths and elastic properties differing with temperature. So, here you see the comparison between elastic properties, yield strength of the material of ceramics, metals, polymers and composites. So, the yield strength is maximum with diamond ceramics. With composites, the yield strength is very high. I was talking about reducing the weight of the component by increasing the strength to weight ratio. So, if the yield strength is high, which we saw here, and if the weight is low, as we saw in the previous slide, because the density of composites is low, then we have a very good chance of making lightweight components with the same strength. So here we have ceramics which are not ductile, which do not have any toughness. Here also you do not have, you may not have too much of toughness, but then that toughness can be built by including appropriate constituents. You have polymers again which do not have any, again which have got completely different behavior with respect to loading compared to metals. So you have metals in a wide range of yield strengths depending on how much you can alloy them, and therefore you can tailor the metals to different strain ranges starting with 0, 10 to the power 0 to 10 to the power 3. So or something more than 10 to the power 3 MPa in strength, yield strength. So here you see that the temperature affects the elastic properties. You have tungsten which has got a very high modulus of elasticity, and it is retained at high temperatures, and that is the reason why it is used for high temperature application. So it is called as a refractory alloy, whereas steel and aluminum are not so good in resisting temperature when it comes to the Young's modulus. So you see that aluminum as it is has got a low Young's modulus which diminishes very rapidly with temperature. So this is a good material for hot working or high temperature deformation, whereas tungsten is a good material for high temperature structural applications. Now we solve a small problem, calculate the elastic elongation. You have delta L by L naught corresponding to the strain of strain on a 305 mm copper piece, which is pulled within the elastic regime, okay, under a stress of 276 MPa. So your Young's modulus is given, and so you have the sigma by Young's modulus equal to strain, right. So this is sigma divided by Young's modulus, that is the strain, and then elastic strain. So delta L by L naught is the value of elastic strain, and so delta L is obtained by multiplying this by L naught, which is 305 millimeters, and therefore the elastic elongation is 0.77 millimeters. So we have seen this, we have seen that you have seen the energy absorbed by the material during the course of forming. We say that you have elastic and plastic regimes of deformation. So if your deformation is in the elastic regime, let us say up to the yield strength itself, then you would have under elastic deformation so much of energy that would be stored. So UR, that is the energy stored in the material in elastic condition, is equal to sigma into d epsilon. Mind you, this is the recoverable elastic energy, because once you remove the load, the strain becomes 0, and the entire elastic deformation also the stress also becomes 0, the strain becomes 0, and therefore the entire energy is therefore recovered. So under load you have certain amount of strain energy in the material, under no load the energy is exactly 0. So that is why this is a right angle triangle, a nice right angle triangle, and therefore sigma integral sigma d epsilon is essentially 1/2 of sigma y into epsilon y as the area of this triangle, which gives you the energy that is stored under elastic conditions. And so you this is the energy under elastic conditions, sigma y square upon 2e. So if the Young's modulus is practically 0, then you have very large amount of elastic energy stored in the material given a constant sigma y. So as the Young's modulus E, for example, becomes smaller and smaller, you have a greater amount of energy that is stored. If E is increased, as in case of infinite stiffness machine, so E is very large for an infinite stiffness type of material, then this stored energy will be practically 0, because regardless of how much is sigma y, the E being practically infinite, the UR will become 0. So you can imagine a line just going here, and that will have practically 0 area. So ideally we do not want any elastic storage of energy, particularly when when we are designing machine elements, but then practical materials have certain finite Young's modulus due to which elastic strains are inevitable. So, we use this for say springs. You have these leaf springs which are made for heavy duty applications, or you have railway coaches which have got coiled springs. So, these springs would be required to store elastic energy, and so that is where this figure, which is elastic energy per unit volume, this is elastic energy per unit volume. Higher it is, better it is for spring manufacture or spring type of applications. So, stored elastic energy for spring type of material is good. For other applications where you do not want it to be springy, you would not want this value of UR to be very high. So, it all depends on application. Similarly, when you go to a clothing shop, the clothes are hung with the help of clips. So, these clips are essentially elastic in nature, in the sense you press them, they open up, and when you release them they exert certain amount of pressure on the cloth so that it does not fall down. So, now there the certain amount of elastic energy has to be stored, and so normally spring steels, so called spring steels, are made with addition of some silicon which promotes this kind of springiness in the material. So, silicon steels are well known for applications to spring type of applications. So, you see here different mechanical behavior which we have already discussed. You have the typical of mild steel here, you have tungsten carbide, plaster of Paris. So, this and this are all brittle in nature, and then here you have elastic deformation of a large extent due to uncoiling of polymer chains. So, we have seen all these things before, and the indices of ductility are percentage elongation and reduction in area, because the percentage elongation is not really an extent of or percentage elongation is not real estimate of ductility, because the cross section, the size effects influence this a lot. So, if your sample is microns thick, for the same material you will get a much lesser percentage of elongation. For a thicker material you will get more percentage elongation. So, this is influenced by size effect. So, if you look at the value of n, that is strain hardening exponent, that is a much better estimate of ductility and index of ductility, because that tells you the extent of uniform strain that you are going to get in a plastic deformation regime. Because now if you take a ductile material like what was shown before, so this is a ductile material. If you take a ductile material, then it deforms a lot in the plastic regime. The permanent deformation is a lot, and then thereafter it fails. Now at this point you get or up to this point you get very uniform deformation. So this is the work hardening regime as it is called, and you get uniform deformation up to this point. So all your forming operations should stop within or before this point is reached. So somewhere in between itself, so that you do not result in failure due to imminent localized necking taking. Actually you have diffuse necking here and then a localized necking over here. Here you lose the work hardening capability at UTS, and then you go down in capacity to withstand the load. So here for example you have a higher higher value of n will represent high value of ductility. So what it means here is a large value of n will mean that the material has got greater uniform elongation. So this point shifts to a higher elongation. So that is what it means by having a higher value of n. Now you have reduction in area. So if the material is capable of a greater reduction in area, let us say gold for example gets reduced to a point, at time of failure the area of the sample at failure is area of a point which is 0 practically. So here the reduction in area also refers to the extent of ductility the material can see or the material can undergo. So now the reduction in area combines the effects of strain hardening and strain rate hardening. So, now if you look at the overall reduction in area, I told you that volume remains constant in plastic deformation. So, there will be certain reduction in area during uniform deformation also. So, let us say you have a sample of certain area and certain length. Let us say the length becomes double, the area will become half naturally. So, this will happen during the uniform deformation regime. So, I mean I am assuming that when the length becomes double, there is still uniform deformation going on. So, immediately after that, let us say necking takes place, then the reduction in area takes place further, and then let us say like gold, supposing the material were to fail at a point, then the reduction in area would be sum total of the reduction in area in uniform deformation plus reduction in area during plastic deformation, and you will get practically the entire area. So, 100% would be the reduction in area for materials like gold, because A naught AF is practically 0, and therefore, you will have a very high percentage of reduction of area. So, with a high value of n, you will get a large reduction of area in uniform deformation. If the rate sensitivity, that is m, which refers to viscous effects, is more, then you will get, even after neck formation, even after localized deformation, a large amount of reduction in area. So, the reduction in area, rate of reduction in area with strain becomes more and more gradual as the value of n strain hardening exponent and rate sensitivity index increase. So, you have therefore different materials here which are given with different degrees of ductility, different Young's moduli. So, now how do you check whether the two materials are same or different? You see that the Young's modulus of A and Young's modulus of D is the same. So, these two materials are likely to be the same, these two materials are the same, whereas here this material is much more compliant than any others. E fractures before yielding. So, it is something like a ceramic or like plaster of Paris. So, tungsten carbide is a ceramic, so it is something like that. So, it has got fracture strength, there is no yielding, whereas D is which has got a high strength. So, this is basically like a high alloy steel which has got very small amount of ductility and very high tensile strength. So, this is high strength steel, whereas here the strength is low, although the steel although the Young's modulus is the same at 210 MPa. C is a material in between, it has got 310 GPa as the Young's modulus and an intermediate strength. So, the ratio of tensile strength to the yield strength is an indicator of the relative strain in uniform deformation. So, if the difference is very high, then you will get a good strain under uniform deformation. If the ratio is very small, then you are likely to get failure at a relatively low strains. Now, if you look at the strain at fracture, you have 340 and 310. So, the rate of work hardening is extremely small in this case, and then the post uniform deformation and uniform deformation together would lead to this combined value. B is a very ductile material, it has got the minimum yield strength and therefore, it has got a very high strain at failure, whereas the other two high strain materials C and D have got practically the same strain at fracture. So, we distinguish now between the energies. I told you about the energy in which is stored in a material under elastic conditions and it is useful for making springs. So, this is called as resilience. So, elastic energy stored in the material due to the elastic deflection is the resilience, whereas toughness refers to the energy consumed per unit volume of plastic deformation. So, you have integral sigma d epsilon 0 to epsilon. So, in case of elastic energy this will be up to the strain corresponding to the yield point, and so you will have d epsilon will be equal to sigma by E, that is Young's modulus, and so you will get the corresponding equation over here. So, E into epsilon will be sigma, and so E epsilon d epsilon will be for the elastic regime. For the plastic regime you have sigma equal to k epsilon to the power n as the expression for sigma, and so you get k epsilon to the power n plus 1 upon n plus 1 as the energy stored in the material due to plastic deformation. So, sigma epsilon upon n plus 1 is the energy stored in the material due to plastic deformation. So, what does it mean? It means the dislocation density that is increased. So, you have spent certain amount of energy on plastic deformation, some energy got converted into heat and some energy got converted to increase in dislocation. So, increase in dislocations means that the energy was used for increasing the dislocation density in the material as the material work hardened and resulted in plastic strain. So, here up to this strain, let us say this entire area under this curve is the energy per unit volume. Again this is per unit volume, because you see that sigma is force divided by area, d epsilon is delta dl by L, right, dl by L is d epsilon. So, force into dl is the energy divided by A into L. In the denominator you have force divided by area, area and L in the denominator, because you have F upon A and d epsilon by is dl by L. So, F dl upon area into L. So, the denominator has got volume as the term. So, that is the reason why this is energy per unit volume. So, if you have this way you can calculate the amount of volume that is needed to store certain amount of elastic energy. So, per unit volume you can store so much of energy in a given material. So, if you have a spring which is expected to store certain amount of elastic energy, you calculate the volume of the material needed to store that much energy. Similar is the case for a plastic, for forging for example. You want to forge a railway axle or a wheel of a railway train. So, you know how much is the energy that is needed for deforming 1 unit volume of material. You know the volume of the material needed for forging of an axle or the wheel of a railway train. Then you know how much of energy would be required for forging that total energy required for actual forging of the axle or the wheel of the train. So, basically what we are looking at is estimation of the energy that the equipment should deliver to meet the requirements of deformation, plastic deformation of a product like a railway axle or something like that. So, for few materials I have listed out the Holomon constants N and K. So, these are N is this and K is here. So, it all depends upon how the materials behave under room temperature conditions. So, these are all room temperature properties of this alloy. So, now we come to the hardness of the material. The another property of the material is hardness, that is resistance to plastic deformation, and it is related with the permanent deformation. Now, you deform the surface with a Brinell test. You press the ball into the surface as in Brinell test, and then examine the size of the impression. So, load divided by the area will give you the value of stress, and so the under certain amount of force. So, force is fixed here, force is fixed and the area of indentation is measured. So, smaller is the area of indentation, then harder is the material, that is what it means. So, this is under Brinell type of test. So, Vickers and Brinell's follow this same principle, load divided by the area of indentation, whereas Rockwell follows the principle of measuring the depth. So, you have a ball indenter, it could be steel ball or anything else, and you have the you can have a diamond indenter depending on the hardness of the material. For example, ball is used for relatively lower loads, a diamond is used for relatively harder materials and higher loads. So, the depth of indentation gives you the hardness in case of Rockwell test. So, Rockwell test does not depend upon the it does not give you the stress, whereas a Brinell test gives you a stress. So, you can correlate the stress determined by the Brinell test and the yield strength of the material if there is no surface hardening treatment being given. So, if the surface hardness of the material is representative of the bulk properties, then you can even measure the hardness of the material at the surface and take that as the yield strength of the material. I mean, you can correlate that, you can't take that as the yield strength, you can correlate that with the yield strength of the material. So, let us see that, we will see that in a minute. So, these expressions give you the different kinds of loads under different testing conditions and the formula for the hardness. So, you have a formula for BHN, which is essentially the load divided by the area. Same is the case with the Vickers hardness and also the Knoop hardness, which has a different kind of pyramid. So, you have Rockwell hardness scales to designate these the hardness of the material. Instead of talking in terms of millimeters, you have A scale, B scale, C scale and so on, and then you have superficial Rockwell hardness scale as well with much lower loads. So, sometimes you want to measure a micro hardness test. So, you want to find out the hardness of the case carburized layer. So, you do not want to go too deep into it, otherwise what will happen is the indenter will just penetrate through the case and then again measure the hardness of the parent metal. So, you want a superficial hardness for which the Rockwell scale is given for relatively lower loads. You do not apply the loads which are used for a normal Rockwell test, lower loads are used for superficial hardness. So, now the tensile strength and hardness are related. I told you that now this is a Rockwell scale will not relate with this, you have BHN, VPN etc. relating with this. So, tensile strength in MPa increases with the Brinell hardness number, and then you get the different values of hardness for different kinds of materials. So, some illustrative values have been given over here. So, for example, you have a 10 mm ball with 3000 kilograms which is used for cast iron and steel, whereas so for these are for Brinell. Non-ferrous alloys 500 kilos, the materials are very soft. For Rockwell A, B, C, D, E, F, the different kinds of indenters are used and different kinds of loading conditions are used, and they correlate with the properties of the material, whether it is hard or soft. So, high strength steel would require a braille indenter with a higher loading, but very soft materials would require a small ball which is a steel ball which will be loaded to about relatively small loads. So, then we have impact behavior, where you have impact taking place due to under various conditions, and this relates with crack propagation. So, we will discuss this impact behavior separately in the next lecture, because the impact behavior is very important and it tells you how at what rate the crack or any defect in the material is likely to propagate. So, we will discuss in the next class. For now, thank you very much.